So recall that the relation of congruence mod 3 is an equivalence relation on the set of integers. And also recall that it has three equivalence classes: the equivalence class of 0, the equivalence class of 1, and the equivalence class of 2. Now, we used reasoning to figure that out in some of the earlier videos, but the reasoning we used was not unique to the number 3. Similar reasoning would have worked for any natural number n, right? So if this 3 would be a 6, the similar reasoning would produce similar results. So this leads to the following fact: let n be any natural number. Consider the equivalence relation congruence mod n, which is, again, it's a relation on Z. It's an equivalence relation on Z. This relation will have n equivalence classes, and they will be the following. They will be the equivalence class of 0, the equivalence class of 1, the equivalence class of 2, ... all the way through the equivalence class of n minus 1. So for example, consider the equivalence relation of congruence mod 5 on the set of integers. So it will have, according to this fact, it has 5 equivalence classes. This equivalence relation has 5 equivalence classes, and they are the following. So first we have the equivalence class of 0, equivalence class of 1. So again, equivalence class of 1 means everything that is related to 1, meaning everything that is congruent to 1 mod 5. Equivalence class of 2, equivalence class of 3, and the equivalence class of 4. So those are the 5 equivalence classes of the relation of congruence mod 5 on the set of integers. Now, this is just repeating what we just said, but now let's use this in a definition. So let n be any natural number. The integers modulo n, which is a set denoted with z sub n, is the set of equivalence classes of the relation congruence mod n on the set of integers. That is, z sub n is equal to the set of the following equivalence classes: the equivalence class of 0, the equivalence class of 1, ... all the way through the equivalence class of n minus 1, where these are the equivalence classes of the relation congruence mod n. For example, z sub 5 is the set containing 5 equivalence classes, the 5 equivalence classes of congruence mod 5. So that would be the equivalence class of 0, the equivalence class of 1, equivalence class of 2, equivalence class of 3, and the equivalence class of 4. So that is z sub 5. But this is, of course, a more general thing, z sub n, for any natural number n. Okay, so now let's so now we can do something very cool. And what we do is we define addition on elements of z sub n. So if we have z sub n, like z sub 5, we define addition among these elements. So for example, if we have elements A and B, or really the equivalence class of A and the equivalence class of B, and these are 2 elements of z sub n, we add them as follows. The equivalence class of A plus the equivalence class of B is equal to the equivalence class of A plus B. For example, let's use z sub 5. So we have in z sub 5, we have 1, equivalence class of 1, and we have equivalence class of 3. Let's add them. So this is, following our definition of addition, it's the equivalence class of 1 plus 3. In other words, the equivalence class of 4. Now, how about this example? How about the equivalence class of 2 plus the equivalence class of 4? So this should be the equivalence class of 2 plus 4, or the equivalence class of 6. However, in z sub 5, there is no 6, right? So in z sub 5, you have 0, 1, 2, 3, and 4, but there is no 6, at least not explicitly. So we could really write 6 if we really want to, but we want to we would prefer to write it in the simplest form. So how can we write this in a simpler form? So here's the answer. We can write it as the equivalence class of 1. Now you might ask, how in the world does the equivalence class of 6 equal to the equivalence class of 1? Or how do we know that? So here are two things to recall. First of all, recall that if A and B are positive, A is congruent to B mod n means that A and B have the same remainder when divided by n. In other words, in Java, A is congruent to B mod n, and so in Java, that means that A mod n equals B mod n. Therefore, 6 is congruent to 1 mod 5. Why? Because 6 mod 5 equals 1 mod 5. Now, also recall that we had a theorem earlier that the equivalence class of A is equal to the equivalence class of B if and only if A is related to B. Therefore, the equivalence class of 6 is equal to the equivalence class of 1, since we know that 6 is congruent to 1 mod 5. So based on this theorem, since A is related to B, since 6 is congruent to 1 mod 5, therefore, the equivalence class of 6 is equal to the equivalence class of 1. Okay, so the actual answer for this addition, the best answer is this, the equivalence class of 1. Technically, the equivalence class of 6 is also correct because equivalence class of 6 is equal to equivalence class of 1, but you should always write it in the simplest form, which here would be the equivalence class of 1. Now, here is an addition table for z sub 5. So the thing to realize here is that z sub 5, the way we've redefined addition for the elements of z sub 5, it's sort of like its own small little number system. Like we have the big number systems like integers and stuff, but here it's a small number system, just 5 elements, the equivalence class of 0, 1, 2, 3, and 4. And we can add them, we can add up elements. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 0 plus 3 is 3, 0 plus 4 is 4. Now, what about 1 plus 1? So 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4. Now, here when we get to the next one, it's tricky. So 1 plus 4. So 1 plus 4 really should be 5, right? But there is no 5 here. There's just 0 through 4. So the equivalence class of 0 is equal to the equivalence class. I'm sorry, the equivalence class of 5 is equal to the equivalence class of 0. Why? Because we're working in z sub 5. So think mod 5. Think about mod 5, right? So 5 mod 5 is equal to 0 mod 5. And 5 mod 5 is equal to 0 mod 5 in Java, right? So like if you would have a program, 5 mod 5 equals 0 mod 5 is true. Okay. Next row, let's see. 2 plus 0, that's 2. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3, again, initially we get the equivalence class of 5, but that simplifies to the equivalence class of 0. How about 2 plus 4? Right, so that initially we get the equivalence class of 6, but that simplifies to the equivalence class of 1. Why 1? Because 6 mod 5 is equivalent to 1 mod 5. How about this? How about 3? 3 plus 0 is 3. 3 plus 4 is 1. 3 plus 2 is 5, but it becomes 0. 3 plus 3 is 6, but it becomes 1. 3 plus 4 is 7, but it simplifies to 2, and so on. So that's the table for z sub 5. So that's addition. Now we can do a similar thing for multiplication. So we define multiplication on elements a and b of z sub n as follows. We say that the equivalence class of a times the equivalence class of b is equal to the equivalence class of a times b. for some examples. So using z sub 5, what if we do the equivalence class of 1 times the equivalence class of 3? Well, that's the equivalence class of 1 times 3, or the equivalence class of 3. Again, in z sub 5, what if we do the equivalence class of 2 times the equivalence class of 4? So that gives us the equivalence class of 2 times 4, which is the equivalence class of 8. But we want, if we're working in z sub 5, we want something that's between 0 and 4. So what is the equivalence class of 8 equal to in that range? So the answer is it's equal to the equivalence class of 3. How do we know that? So again, the same reason as before. So A mod n should be equal to B mod n. That's what A congruent to B mod n means that A mod n is equal to B mod n. So for example, 8 is congruent to 3 mod 5 because 8 mod 5 is equal to 3 mod 5. And also recall that, as we said before, the equivalence class of A is equal to the equivalence class of B if and only if A is related to B. So since we know that 8 is congruent to 3 mod 5, right? So 8 is related to 3. Therefore, the equivalence class of 8 is equal to the equivalence class of 3. So that's why instead of leaving this as our final answer, we simplify it further and we get this. And then here is the multiplication table for z sub 5. So it gives you the result of multiplication, the simplified result of multiplication for every possible choice of things that you might want to multiply in z sub 5. And for homework, you'll be asked to write similar tables, but instead of z sub 5, maybe it'll be for z sub 4 or z sub 6 or whatever.